Our final topic is what happens when you have too much charge. You can't charge something up forever. Eventually, something is going to give. So let's imagine we have sort of just a curved conductor, and we put some charge on it. But we're not happy. Let's put more charge on it. Let's put a huge amount of charge. And that's what this thing does. This is a Wimshurst generator. So crazy looking machine, kind of looks like a time machine or something. We spin this thing, and these little metal paddles go against these brushes. So the brushes touch the metal and the plastic, and the metal and the plastic, and the metal and the plastic. So they pick up charge from the plastic, and they dump it into the circuit with the metal. So it's very complicated the way it works. The things, you have two counter-rotating wheels, and there's capacitors in here. We're going to get into the details of exactly how it works. But the point is, when you spin it, it takes that mechanical energy and it builds up charge on these two probes here. So one is positive and one is negative. So we have a way to put a huge amount of charge on a surface. So let's think then, what's eventually going to happen is we add more and more charge. Well, the interesting thing that happens is actually not in the metal, it's in the air near the metal. So in the air, what do we have? We have oxygen, we have nitrogen, we have a lot of things. I'm going to pretend we just have neutral air molecules, okay? So let's say we have a nucleus here, and it has some electrons going around it. Neutral air molecule. Now we know, we talked about ions, we know ions can be formed. We know that an electron can be knocked off of an atom. And it can happen for a lot of reasons. One is when it gets really close to this surface, if we think about what happens, all this negative charge is going to make the electrons want to go away. It's going to sort of warp it. The electron clouds, you know, they really don't want to be anywhere near this thing. And the proton, the nucleus really wants to come this way. So the effect of these charges could kind of warp the molecule, the gas molecule. Cosmic rays can come in from space, can ionize the molecule. Basically, somehow, one of these things gets ionized. It just takes one. An electron might actually manage to fly off and go ramming into the gas molecule and create an ion. But somehow, if you can just get one of these things to come apart, you end up with, let's think of what you have, a positive ion and an electron. And now you have these two separate charged objects near all this charge. The electron's going to go flying off that way, feels a huge electrostatic force that way, and the ion will feel a big electrostatic force this way. This happens very close to the electrode at sort of a molecular scale, so the separations are very small. Okay? This thing goes flying off, gets a lot of kinetic energy, in fact enough to ionize another neutral gas molecule. Okay? So if it slams into this, then you can end up making this thing positive and having another electron fly away. And then this goes this way. So if you can just get one to separate, you can get sort of a cascade effect, and then you can have this effect happen in many, many gas molecules near the surface. All right? This is called a corona discharge. And it's interesting because it makes light. So in all these processes, the gas molecules get excited, they go into excited states, and they relax back into ground states. And when they do that, they emit photons, which I'll just kind of draw as these wavy little things. So in regular air, the coronas are due to the excitation and relaxing of, of oxygen and nitrogen, these gases, and it kind of makes kind of a pinkish purple glow. It's a little bit hard to see. It's very hard to see. So I took a picture of one with all the room lights off. So we're showing you that now. And you're seeing the corona discharge above one of these two electrodes, that little glow. And you can see it's not uniformly around the electrode. It's really happening at a little sharp spot near the electrode, because that's where the accumulation of charge is the greatest. But that's not the end of the story. A corona discharge is stable, right? So if we think back here, we have these atoms being ionized, and the electron flies this way, and the atom flies this way, and it happens here. And if you get far enough away, you're getting farther and farther from the electrode, and how much you accelerate this electron is going down. And it eventually gets low enough that it doesn't give you enough energy to create another ion. So the corona discharge kind of happens in a well-defined region. Then outside that region, it stops. And you saw that in the picture. But then something else can happen. This is the positive electrode over here. And if you keep charging it, it gets very positive, very positive, very positive, very positive, very positive. Okay? The same processes can happen on the positive electrode. You can have a gas molecule over here that's neutral, and something can ionize it, and when it becomes ionized and the electron comes off, in this case the ion would fly that way, and the electron would fly that way towards the electrode. So same thing. The rate at which they happen and how bright the lights are actually different because it's not completely symmetric, right? So here, the light thing, the electron is flying away, and the heavy thing, the gas ion, is flying back, and here it's the opposite. So you get corona on both sides, but they're different kinds of coronas. But you get them on both sides. But both of them eventually stop because you get far enough away from the electrode that the forces aren't really big enough to make it happen. But one special thing can happen is if this corona, you can think of it as this coronas get together, you can create a plasma. You can basically create a region of the gas that's basically full of electrons and ions. And it's so full of those that it essentially becomes a conductor. And a huge current goes between the two. This is called an arc discharge, or a lightning bolt is pretty much what you would think of it as. So this machine can actually make, first it can make a corona. You saw a picture of the corona. But then if I turn it fast enough, you'll make an arc. Right? So if you get it going really fast, oh, there's one. So you can see the arcs hopping between the two electrodes on the Wimshurst machine. So this happens when the charge gets so big that it rips molecules apart in the air and makes a conducting path between the two. But it doesn't last, right? It's just a snap and it goes away. And the reason is that it discharges. So it takes a huge amount of charge on those balls, those electrodes, to cause this to happen. But as soon as that huge current flows by, then it's done. Okay? And sometimes they're very pretty. And it's fun to do. Now, for the final demo, for the sequence on charge, I have taught for a while, and I know the main thing that students like to see is they like to see danger, and they like to see the professor in pain. That's really the main thing. So I'm going to use this for one more demo. I told you before that your body is a conductor. You're a leaky bag of salt water. Right? So salt water is a conductor, ions can move, your body is mostly full of salty water. Your skin is wet, so you are a conductor. So if I'm a conductor, the lightning bolt should go through my finger. Okay, so I'm going to hold my finger in here, and we're going to send the lightning through. And I think on a few shots, you'll be able to see it literally going in one side of my finger and out the other. Sometimes it goes around, but it often goes through. So there you go. Now you're happy. I'm glad I missed that one. All right, I'll see you in the next section.